Okay, our second guided notes video is part 2 of lesson 1, and yes, the Earth itself is a magnet. So the Earth has a magnetic field, generates a magnetic field, and one of the things I definitely want you to get down into your notes is the fact that the north magnetic field, so we said that the field lines come out of north and go into south, is really in the inverted geographic north and south. So the North Pole is south magnetic, and the north magnetic pole is Antarctica, south geographic. So where does the magnetic field of the Earth come from? Well, it comes from moving cues. Moving charge makes magnetic field. So the exact mechanism is difficult for us to understand, and to understand precisely, we would have to be able to see through the Earth and look at the movement of the charges. So it's attributed, scientists believe, to the molten core of the Earth in motion as the Earth spins. And you may have heard that the magnetic field of the Earth does flip orientation. And yes, that is true, it does. And that would only be true if the moving cues flip their motion. So we're not going to talk in detail about the Earth's magnetic field, because we have a lot to learn about the basic generation of the magnetic field and magnetic field effects. But I think it is important, since we live on a big magnet, to understand something about the magnetic field, and the fact that it comes from the moving charges in the molten core and the spinning of the Earth, I think, is important. Now, the actual magnetic field of the Earth is a little more complicated than just the magnetic field that the Earth generates itself, because the actual magnetic field, and I don't like of here, put around. So the actual magnetic field around the Earth is a combined effect of the moving charges from the solar wind. And what is the solar wind? Well, the solar wind is these moving cues, right? So it's still moving charges, but high energy electrons, protons, alpha particles, which are helium nucleus, the helium stripped of the electrons streaming in from the sun. And by the way, these high energy particles are very dangerous to human life in terms of these impacting biological systems. And we have the protection. We'll see more in this chapter how it is that the magnetic field of the Earth deflects these particles. So it's a complicated kind of overall scenario that's going on here, because the charged particles themselves from the solar wind make magnetic field that combines to have a net magnetic field. Remember, fields are vector quantities, so we have to do a vector addition of all the field lines to get the net magnetic field. But the overall effect that we see in the field around the Earth is that you get this tail in the magnetic field. So those magnetic field lines, let me change my color here. The magnetic field lines get pulled out. Actually, they come into south, if we're keeping our orientation. Get pulled out and stretched out on the far side from the sun and compressed on the near side of the sun. And we will talk about how it is that charged particles interact with magnetic fields and are deflected, and how it is that the charged particles from the solar wind ionize the atmosphere and end up spiraling around the magnetic field of the Earth, and their ionization of the atmosphere generates the northern lights, those beautiful northern lights that we see. So you will understand more about how that occurs by understanding the effect of the magnetic field on moving charges. Because just like with electric fields, where we had source charges that make electric field, and then we had charges that were influenced by the electric field. We have the same thing for magnetism. We have source charges that make the magnetic field, the moving Qs, the moving source Qs that make the magnetic field, and then we'll have charges, Q, that are placed in those magnetic fields and injected into the magnetic fields, and talk about their movement as well. Well, the last part of this lesson is really just a reminder, for the most part, that we have a vector nature of the magnetic fields that follows all the rules of our vectors, that we have strong magnetic fields, always going from north into south, and the field lines close together would represent a strong field. A weak field is indicated by the field line spacing further apart. And we also observe that a north and south pole of a permanent magnet will attract each other, and a north and north pole and a south and south pole will repel each other. So our basic notion of field lines for magnetic fields beginning on north and going into south, or coming out of north, I'm sorry, not beginning, coming out of north and going into south remains. So we don't have a definitive beginning and a definitive end. But if we have a north and a south together, we observe that there is a force pulling those two magnets together, and we see that the north and the south and the south will repel each other. So that's our basic introduction, these first 2 pages. And we are going to go on now to introducing equations and talk about source charges and Qs that are affected by the magnetic field that those source charges make, and I think get a better understanding and feel for magnetic fields and what they do.